Hello everyone, my name is Mohammed Noor Awad, a researcher and a PhD student from Itma University. Today I'll be presenting our work about pre-filtering code suggestions using developer behavioral telemetry to optimize LLM-assisted programming. This work is prepared by my colleagues Sergey Ivanov and Olga Tifanova. So as we know, IDE copilots like GitHub Copilot or Cursor IDE, for example, they surface a lot of code autocomplete suggestions. But in real development session, most of them are actually ignored. This actually means two things. First, it's a compute waste since like every suggestion triggers like a GPU inference call, which is expensive. And secondly, it has an attention cost as like each unwanted suggestion interrupt the developer's flow. So current systems mainly focus on what to suggest, like example can be improving the ranking of the autocomplete suggestions or like the retrieval of extra context. So generally they focus on what to suggest, but they don't actually solve the issue of when to show these suggestions. So previous work showed like some systems use fixed timers or static heuristics that don't adapt to the developer's moment-to-moment state, like whether they are deeply typing, debugging, or just exploring. So our guiding questions become like, can we decide before calling the LLM whether it's even worth showing a suggestion? So our main idea behind this approach is actually straightforward. We continuously capture real-time IDE telemetry, things like typing speed, navigation actions, command usage, historical acceptance of the suggestions, and we use it to train a lightweight classifier that predicts a single question. Will the next suggestion be accepted? So when the model predicts a low probability for the current request, we simply suppress the LLM call. No prompt is sent, no GPU cycles are wasted, and the developer isn't interrupted, which is like a big gain. So our benefits here came from like reducing the compute load by skipping low value suggestions and actually improving the user experience by surfacing like fewer but like better timed suggestions. Uh, we actually chose to rely only on behavioral telemetry for some key reasons. First, it's like available before inference, which makes it perfect for real-time gating. So we can decide before spending any GPU resources. And secondly, it's private by design. So it doesn't depend on the code or the prompt. So there is no risk of leaking the developer's content. And actually, it like generalizes well. So the same behavioral signals like typing or navigation, they appear like in any IDE or programming language. And finally, it's interpretable. So features such as like typing rhyme, command usage, or error count map naturally to the developer's readiness. So what makes this different from earlier work is that we move telemetry from post-hook analytics to like real-time decision about whether to even call the LLM. So our focus is on when the developer can be interrupted, not just like improving the model suggestions. And here we see how the full system works, specifically the pre-filtering gate. So it starts with the VS Code plugin that continuously captures behavioral telemetry, as we mentioned, historical acceptance, typing pace, like etc. So these signals are passed to the behavioral classifier that estimates the probability of a suggestion being accepted. So if that probability is above like a certain threshold, the request continues to the LLM. Otherwise, the request is simply like suppressed, saving like GPU and network cost. So like effectively, the pre-filter kit acts like a decision layer sitting between the IDE and the model, which is like hopefully or like our goal is to make it like fast, private, and language agnostic module. So the feature that our model uses are entirely behavioral, as we mentioned, and computed before the LLM is called. So this means that no code or prompt are ever inspected or stored, which like keeps the system both like fast and privacy safe. So it's also model agnostic. So the filter can sit in front of any backend, regardless of the programming language or the model type, which makes it like a true drop-in like component, which can be plugged in any other plugin. And also, it's interpretable and lightweight, so the feature correspond like to natural IDE actions, so they're like easy to reason whether it's like correct or like not correct, and quick enough for real-time decisions. And the table here shows like our main groups of signals. Like we categorize them into like 5 categories: fluency, code editing, command usage, code state, and like session context. Each of those categories actually reflect a different aspect of the developer's behavior and engagement. So all these signals are computed from how the developer like interacts with the IDE, not like what they are actually doing. And to train the pre-filter, we framed it like as a binary classification task, so predicting whether the suggestion will be accepted or not. So it's a classic binary classification task. Um, and we trained it on our like data set. So our data set combined around like 23 suggestion events, out of which there are like around 400 acceptance. So the classes were like largely imbalanced at around like 1 to 4.4. And we examined like several lightweight three models, and among them, Catboost performed best under class imbalance with like the best precision recall trade-offs, while staying actually compact enough to run directly in the VS Code plugin. Yeah, so we trained it using the weighted binary cross entropy loss to counter the imbalancing. So the focus is like on confidently filtering out the low value suggestion, like rather than maximizing frequency, accuracy. I mean. So yeah, the offline evaluation on our held out test set shows that the model performed well, giving the class imbalance. It shows like solid discrimination and well calibrated probability outputs. And in our case, we operated the model at the threshold of zero point 0.1. So at this point, we filtered out around 40% of the rejected suggestions before even calling the LLM, like an almost perfect precision score, while we missed around like 3% of true accepts, but it's still like very high recall. So yeah, and here the shape plot on the right shows like the most influential behavioral features are mainly like recent acceptance ratio, number of accepted suggestions, the length of the current file, for example. So yeah, it's a good enough model that operates at the gate, like offering low cost decisions before like expensive inference. So after validating the model offline, we deployed it actually in real VS Code environment for a few months. It's actually our VS Code internal tool. We invited developers, out of which some of them like they responded and they use it in their daily work. So before introducing the whole filter, we had like around 18% acceptance rate, and after enabling the behavioral gate, a big chunk of around like 35% of calls were like suppressed directly before inference. And among the remaining ones, the acceptance rate jumped to around like 34%, which is pretty big jump for us. So overall, we achieved an absolute gain of like 16% almost, and around 86% relative improvement, while cutting backend load by roughly like 35%, which is like very good saving. So we nearly doubled useful completions while reducing GPU usage, all without like changing the LLM itself. And here we see how the filter behaves. So we inspect like a 4 hours long session trace of like one of our developers. So you can see that the system dynamically switches between allowing filtering, like jumps like back and forth, depending on the developer's activity. So it works because the developer actually has what we call readiness momentum. So when a developer recently accepted a few suggestions, they are more likely to accept the next one. And when they are like typing rapidly, making a lot of like quick fixes or like just deleting a lot of things, it's probably better not to like interrupt them or suggest anything. So as a result, we saved like GPU and network resources, and we reduced like the queue time on our backend, while the user saw like fewer but more relevant suggestions, which means like less annoyance and smoother focus. And here we see like a demo of our plugin. It shows like how timely the suggestions are. So we basically use our plugin to do our other projects. So yeah, this should give like an idea of the capabilities of our plugin. And to wrap up, we note that our behavioral filter like helped our plugin like to achieve 34% suggestion acceptance and saved 35% of LLM calls, and we did so while inspecting 0 lines of code. So in this work, we proposed a behavioral only pre-filter that like predicts suggestions acceptance before invoking the LLM, which is like actually a critical idea. Is that like we are doing everything before calling the LLM. So it relies entirely on real-time IDE telemetry, which makes it like privacy preserving tool, and also language agnostic, as we mentioned, and light enough to run inside a production plugin. And we demonstrated that significant efficiency and usability gains can be like achieved without changing the LLM itself, without touching the backend, only by optimizing the timing of when suggestions are triggered. So looking ahead, our next steps are to add like a light contextual signals while like keeping the same privacy guarantees, and also to enable like per developer adaptive threshold that evolves like with their behavior over time, maybe like auto train, for example. So yeah, like we again state that the pre-filter technique gives us like a simple but true powerful way to make code assistants smarter about when to show these suggestions or when to offer their help. So yeah, that's it. Thank you all for your attention.